This is the extra multiple choice questions from December 2020. Just turn them just like it's going to be happening this week in 2023. So the distance between opposite corners of a cube is 2, so this distance across here is 2. There's a cube, so you can call every side x, and then hopefully you've done 3D Pythagoras the correct way, where you literally just say x squared plus x squared plus x squared is 2 squared, so therefore 3x squared is 4, and then divide and then square root. Except you don't really even have to square root because you're looking for the surface area, which is, or each side is of course x squared, so the surface area is 6x squared, so just times this by 6, and you get the answer of 8. If you don't know this formula for Pythagoras, maybe your teacher taught you x squared plus x squared rooted, and you get this bit, and then you do another lot of Pythagoras with this inner triangle here. But this is just better, so just do that. Anyway, part B, after that nice little warm-up, put all the negative powers down below in a fraction like this, and all the positive ones above, and then just split every fraction downwards. So 2/3, and then 4/5, and so on. They're all to the power x, so you can just factorize or sort of undistribute the x out like this. And now all of these numbers here, all the way to the end, are all lower than 1. And when you raise something lower than 1 to a very big number, you get something very close to 0. And when you times lots of things that are very close to 0 together, you get something very, very close to 0. So I think that's what we can argue on that question there. Cos inverse of a half in degrees is 60, except it's not. It could also be minus 60, because cos is symmetrical. So it could also be minus 60, or it could be 360 minus 60, which is 300, or it could be minus 300. Those are just the ones that I decided to go with first. You can also use cast diagrams if you're weird. To do that, cross multiply this out, and divide by 60, of course, and you get a solution at x is equals 2 only. So that's pretty cool. And then you try this one. So we've got one solution so far. Of course, there are an infinite number of things I could write for these four, but I don't want to do that. So I just decided to go with this one, see what happens, go with this one, see what happens, and so on, and see whether there's any reason the others don't make it. So okay, times this across, divide by 60 again. You get this. This has b squared minus 4c less than 0. You can verify 16 minus 100. So okay, that's got no solutions. What about this one here? So cross multiply this one out, rearrange it, divide by 60. Solution at minus 2, of course. Only solution there, so we've got 2 solutions so far. And now this one also has a discriminant less than 0. And what I'm going to argue here is that all of the other solutions going along that sine line, or cos line that we're doing, make this number bigger, which in turn, when that times by x squared plus 4, that essentially increases the a and the c value in b squared minus 4ac. But of course, if you increase the a and the c, you're taking away more stuff, and so the discriminant is going to be less than 0. So I think I can argue that the only 2 solutions are the 2 that I found so far, and all the other ones are just going to have negative discriminant. And so 2, I think, is the answer. So the coefficient of each term here is the nth prime number. So it's 2, 3, 5, next one will be 7, next one will be 5, next one will be 11. And now I've differentiated this, because if I differentiate 5 times, so okay, if you differentiate once, this becomes the constant. Twice, this becomes the constant. 3 times, this becomes the constant. The reason I'm only talking about the constant is because when you put in x as 0, the only thing that's going to remain is the constant in a polynomial, right? When you put in 0, everything goes away except for the constant. So we just need to track which is what. So if this is the constant after 1 differentiation, this will be after 2, this will be after 3, this will be after 4, and this will be the constant after 5. And that's after deriving by doing 11 times 5, bring the 4 down times 4, bring the 3 down times 2, times 1, and so on. And so you're just going to have, after you derive 5 times, this number, after deriving this from 5 times, plus some function of x that has no constant in it. So when you put 0 in, this just goes away, and you're just left with this. Of course, 5 factorial is 120, and you can just tell that this is a bit bigger than 1,100, of course. And so the only one that's reasonable is this one here, without actually calculating it. Very simple to do these kind of questions. Does the graph go through 0, 0? 0 minus 0 is not 1, so no. Does the graph go through 1, 0? Well, 1 minus 0 is 1, so it does go through 1, 0, so no. And okay, that's it. Does it go through 0, 1? Well, 0 minus 1 is not 1, so it does not go through 0, 1, so we'll get rid of this. What's the only difference between these two? Well, does it go through minus 1, 0? Well, minus 1 to the power 20 is 1, minus 0 is 1, so it does, which this one doesn't, so that can't be answered. The answer is D. Nice and straightforward. Now, I'm a bit unsure what the proper solution for this is, if you've done like FP1, FP2, you know how to evaluate inequalities like this. Basically, you can't times by x minus 2. And the reason that you can't do that is because x minus 2 might be negative, which therefore might flip this sign here. So what I'm going to do is I'm going to times by x plus 2 squared, because x plus 2 squared is a positive or zero number, which means that when I do that, this inequality will not flip. So this becomes x squared minus 1 times, well, one of these will cancel with one of those. So times x plus 2 less than 0, because of course 0 doesn't change. But of course I can factorize this, difference of two squares. Now this is just a cubic with roots 1, minus 1, and minus 2. So minus 2, minus 1, and 1 here. And when is that cubic less than 0? When it's less than minus 2 and between 1 and minus 1. So that's what I've got this inequality to become. So let's replace that there. And the same thing here. So times by 1 minus x all squared. That way you're not flipping this sign. You get this. This is a quadratic with roots at 1 and minus 1, except of course it's upside down. So it looks like this. It's bigger than 0 between 1 and minus 1. Now, this means that if you are in Q, if Q is true, then P is true, because you're between minus 1 and 1, which is a thing that P does as well. But if P is true, you could be like minus 3, and therefore Q isn't. So Q implies P, but P does not imply Q is the correct answer. G then, so I just decided, you start with 0. I decided to do S a bunch of times and see what happens. If you do that, you get 0, and then you get 1 when you do an S, and then you put 1 in, and you get 2, and then you put 2 in, and you get 3, and so on. You just end up increasing 1 every time. So that's not very interesting. What happens if you just do T a bunch of times? Well, you put in 0, and you get out minus 1. And then you put in minus 1, and you get half times minus 1 is minus a half, minus 1 is minus 3 over 2. Then you put in minus 3 over 2, you get minus 3 over 4. Minus 1 is minus 7 over 4. Then you do it again, times that by half is minus 7 eighths, minus 1 is minus 15 eighths. And okay, let's have a look then. So the set of possible outputs is not all possible rational whole numbers, or positive, because we've got some negatives here. So it can't be that, and it can't be this. It also can't be this, because I've found some that are less than minus 1. And it can't be this, because this talks about positives again. So it's one of these two things. Is it all rational numbers with denominator power 2 written in lowest terms? I guess these have denominator power 2, because they're like 2 to the power 0. Or it could be this, rational numbers greater than minus 2. I mean, this isn't minus 2. So let's just keep going. If we put in this again, we get minus 15 over 16 minus 1 is minus 31 over 16. That's still not minus 2. It's getting suspiciously close. If we do it one more time, times by half, you get minus 31 over 32. And then you take away 1, which is minus 32 over 32. You get minus 63 over 32. And at this point, I'm pretty confident this is just limiting to minus 2. And so this feels like the right answer. You can also logically argue that if you put in something slightly less than minus 2, or slightly like something like minus 1.99, you halve it to get something ever so slightly less than minus 1 in terms of being minus 0.999. And when you take away 1, you're still just going to end up with something slightly towards 0 from 2 again. And then you just do it again and again and again, and you just end up getting closer and closer to. So I think this is fairly logical. I think that will be the answer. This question was super easy. A0 is A, so you just put A in there and you get A1 is A squared. Then you put in A1 in here, so you get A squared squared, which is A to the 4, and then A to the 4 squared is A to the 8, and so on. Then you do the same for Bn, but Bn is log 2 of An, so B0 is log 2 A0, which is log 2 big A. B1 is log 2 of A squared, which is 2 log to base 2 of A, and so on. You can put all the powers down, and you end up with this here. You just times this, and so on. So it's just a geometric series, times by 2, times by 4. Times by 2, times by 2, times by 2. So it's just a geometric progression, I believe. And that's all we have to say. This question was really interesting. You've got an equilateral triangle, 1,000 across here. And now what I decided to do is, so this is 500, this is 1,000. I always have the 1 root 3 over 2 triangle in my head. So I just scaled it up by a factor of 1,000. And you get 500 root 3 there. So that's fine, because the length is 1,000, right? Did I misspeak there? It's the 1 root 3 over 2 triangle. I'm not making that up. That is a triangle, right? 1 squared plus 3/4. No, it's not. Is it 1 root 3 2? Is that a triangle? Am I just being an idiot? It is, right? 1 root 3 2. And then you times it by 500 and you get 500 root 3 here. That's what I was saying. Okay, anyway, what I decided to do here was draw a box of 1,000 around it. And now I'm going to argue that this box has roughly a million dots inside of it. It doesn't actually, because it has a load of dots going around the outside that we shouldn't be counting. But it roughly has this many dots inside of it, take away a few thousands. So, okay. Now, this equilateral triangle is clearly not 86% of this square. Like, it's just not. I think it's obvious. I'm just going to assert that it's not. So I'm going to get rid of all of these answers and then decide that it's actually around 43% of it, which looks more reasonable. Now, these two answers are very close together. So this is one of those times where I don't really want to calculate which one of these it is, because that would be ridiculous. So what I need to do is just look at these two answers that I've got it down to and decide what is most different about them and try and figure out whether there's some way that I could use that fact to identify which one it's not. So one of these is even and one of them is odd. So if I could somehow figure out whether or not there's an odd or even number of dots in this triangle, that would immediately tell me which one the answer was. Now I look at this hint, root 3 is this. I decided to use that. So obviously 1,000 root 3 is this, which means 500 root 3 is that. Now what that means is that this point of the triangle is just a shade above the 866th dot that makes up this line. So there are 866 dots on this line here. Now this is where you have to be really, really, really intelligent. There's some number of dots in this part of the triangle, not including, of course, any of the outside edges. But the same number of dots are over here because of the symmetry. So if there were an odd number of dots on this side, there were the same odd number of dots on this side, which add up to make an even number, and then the line in the middle is an even number. So that, of course, adds up for an even. And of course, if there's an even here, there's an even here, there's an even here, that adds to an even. In any case, you're going to get an even number of dots, and so the answer must be this. And I think that was quite a tough question, but yeah, cool. This is also quite a tough question. You just need to know what some of these graphs look like, I think. So if we rearrange this, we get this, which is clearly this graph here, and we want to be above the quadratic for this. Rearrange this, and we get this one here, which is the upside down one, and we want to be below it, so we want to be in this area that I'm sketching pretty terribly right here. Now this one here is, and you might not have seen this before, I chose to write it like this because essentially, if you just swap out the x and the y's for each other, you get y greater than x squared minus 2, which we've already written. So one way to plot things like this is to say, well, okay, it's the same as this, you've just swapped the x and the y's over. Swapping the x and the y's over is the same as a reflection in the line y equals x. So this graph, which was this one, if I reflect it in the line y equals x, I'm going to get a graph that's sideways like this. And so that looks like this. I can also say about it, of course, that when y is 0, x is minus 2, so that's at minus 2 there. These graphs, notice, have a roots at root 2, which is closer to the origin, obviously, than 2 is. And you can make the same argument up here. When x is 0, y is root 2. But here, when x is 0, y is 2 and minus 2, right? So this one has a lower y-intercept than these two do. Exactly the same for this drawing here. It's just the other one reflected, and so it looks like this. Same logic about the intercepts. This is a terrible drawing, so I just decided to make a computer. It gets you this. One thing to really notice here is that all the graphs go through some version of 1, 1, whether it's minus 1, 1, or 1, minus 1, 1, or 1, 1, or minus 1, minus 1. All 4 of the graphs go through 2 of them, which is really helpful because what I then decided was, okay, we just got a box here of area 4. So the answer is a bit above 4, is the area enclosed by all of these, inside all of these. So, okay, it could be this, except I don't understand where pi is going to come from. Pi comes out a lot, but it's not going to be from here. It's not going to be this, obviously. It's not going to be this. This is, I mean, what is this? Like 9 point something? Too big. The answer is obviously this. And I don't need to calculate it. The answers just tell me that it's this because it's clearly a bit bigger than 4. If you actually want to calculate it, you can just take one of these lines. I think I took the blue one and just integrated between roots 2 and 1 to find this little triangular-ish like shape, which isn't a triangle, of course, because these are curves. And then I'm just going to times the answer by 8. So this is just me doing some boring maths. You just integrate, you put the numbers in, you times the answer by 8 and you add the original 4, and of course it cleans up and you get exactly this. But always look out for the answers, because you could have just circled this pretty much immediately after drawing the sketch, as long as you understood what these graphs actually look like. This whole business of swapping the x and y's being a reflection of the line y intersect is very useful. So maybe also bear that in mind. Anyway, thanks for watching. Good luck next week.